Right, so the last question. Label them off again. So part 1. Just go underneath. Part 1 is state the laws of equilibrium. So the first law is the upward forces equal the downward forces. And the second law is that the clockwise moments equal the anti-clockwise moments. And I will get the, I'll get the marking scheme at the end, so just give me a second. My laptop has died. So, second question. A sign weighing 400 newtons is suspended at the end of a uniform horizontal rod. The rod touches the wall at position X. The rod weighs 330 newtons and is 1.2 meters long. A support cable makes an angle of 35 with the rod. Okay, calculate the clockwise moments due to the weight of the sign. Okay, so the weight of the rod, the 330, is going to act here. Halfway, so this is 60 centimeters and then this is 60 centimeters. And both of these, if that's my fixed point, both of these are clockwise moments. So it is, to calculate the clockwise moments, it is force by distance for the 330. So it's 330 multiplied by 0.6 away from the fulcrum. And then the other one is 400 by 1.2 away from the fulcrum. So if we figure that out, 0.6 plus 400 by 1.2, I get 678 for the clockwise moments and 64. That is moments, so newton meters. Doesn't look like an 8. Okay. Hence, calculate the tension in the cable. Okay, so it's obviously at an angle, so we're going to have to use vectors. So like earlier, if we can find this one. Okay, so like pretend that one doesn't exist and it's been supported by the red one. We know that it's in equilibrium, which means we know that the clockwise moments equal the anti-clockwise moments. So we're going to say that this is an anti-clockwise moment. So we're pretending the one at the angle doesn't exist. Now, obviously, not for long, but that's what we're doing for now. Okay, so the clockwise moments was 678. The anti-clockwise moment is some force we don't know multiplied by the distance, and the distance from the fulcrum is 1.2. So if I divide that by 1.2 and divide by 1.2, I get that the force is 678 divided by 1.2. The force is 565 newtons. Right, so this is 565 newtons. Okay. So if we take this to be the diagonal, so this is like your resultant, and then you've got your two perpendicular vectors. Yeah, so this is the vertical one, And then this one down here is the horizontal one. Can finish off my parallelogram. If this is 35, then this has to be 55. 90 minus 35, so 55. And this is the opposites. This is the hypotenuse because the right angle is here, making this the adjacent. Eliminate one, so I'm going to eliminate the opposite. So it's adjacent and hypotenuse, which is cos. Is that right? Am I doing that right? Let's give it a go. So the cos of 55 equals adjacent over, oh, no, I know the, whatever, keep going. Adjacent over hypotenuse, I actually know the adjacent. So the cos of 55 equals, the adjacent is 565. So it's 565 over the hypotenuse. Multiply across by the hypotenuse, multiply across by the hypotenuse. So that gives us the hypotenuse times the cos of 55 equals 565. And then you divide by the cos of 55 and divide by the cos of 55. So the hypotenuse, which is the one we're looking for, is 565 divided by the cos of 55, which is 985 newtons is the tension in the cable. So I have the marking scheme here now. So this here was 6 plus 3. So first one correct 6, second one correct 3. And it doesn't matter which one was first, if that makes sense. So if you only got the second one correct, you would still get 6 marks. The 678 is 3 for doing force by distance, 3 for doing the calculation, and then 3 for the answer. And then this last one was 3 for getting the 565, 3 for getting the answer. And then the final part, the rotating object can be in equilibrium. How can this happen? So basically it's moving at a constant velocity in a circle. Yeah, so the forces are balanced. They're not speeding up, not slowing down. It's moving at a constant velocity. It's just doing so in a rotational way. And that's worth 4. All right, so that is finally the whole test done. So take your time, go through it and let me know.